Thank you very much, and I'm delighted to talk to you today about Maxwell's work on Saturn's rings and to try to make some connections with ideas of gravitational instability and the formation of planets in our solar system and beyond. So, as others have mentioned, Maxwell was motivated to work on Saturn's rings because of the Adams Prize essay competition for 1856, which was announced in this way, and the emphasis was on the stability of the rings. It wasn't known at the time whether they were solid or fluid, and various possibilities were to be investigated. Well, the Adams Prize had been established a few years before to honor John Couch Adams, the mathematical astronomer from Cornwall, who had graduated in 1843 and become a fellow of St. John's College. And he'd worked analyzing the discrepancies in the orbit of Uranus and used that to predict the existence and the location of another planet, which would be Neptune, except, as is well known, the British astronomers at the time failed to capitalize on the opportunity, and instead the Neptune was discovered following Leverrier's parallel and independent calculations. Anyway, the Adams Prize was to be awarded every 2 years to a Cambridge graduate in those days for the best essay on some topic in pure mathematics, astronomy, or another branch of natural philosophy. And the first topic for the Adams Prize was a very Adams-like topic and was won by Robert Pearson from St. John's. But then after that, well, the next one wasn't awarded at all. And then a couple of years after that, actually there were no candidates for the essay competition. So when it came to 1856, well, perhaps the topic was more inviting. Maxwell won the essay, of course, the essay competition this year, of course, but his was the only entry in the competition. Now, two of the examiners for the Adams Prize for 1856 were James Challis, who was Plumian Professor of Astronomy, Director of the Observatory at Cambridge, and was one of the people that famously failed to follow up on Adams' calculations and missed the opportunity to discover Neptune. And then William Thomson, later Lord Kelvin, who a few years older than Maxwell, but was already professor in Glasgow. And how did this fit into Maxwell's own timeline? He'd recently graduated in mathematics, as we've heard, coming second in the tripos, and had received a fellowship at Trinity College. He was reading his paper on Faraday's lines of force to this society in the year 1855 when the essay topic was announced. Now, the following year, he had to return to Scotland, and his father passed away. And also at this time, he was being considered for the chair in natural philosophy at Marischal College, Aberdeen, which he took up at the end of 1856. So it's during this period that he was working on Saturn's rings, and he had to complete the essay by the end of that year. And then he received the prize the following summer, but actually the published version of the essay contains some additional work and some corrections, which involves some correspondence with Thomson. Well, in 1856, Saturn's rings had already been known for 200 years or more. Well, when Galileo turned his new telescope to Saturn, he recorded his discovery in this anagram, which was later revealed to be this Latin phrase, meaning that I have observed the most distant planet to have a triple form. But as the diagram suggests, Galileo thought that the planet had ears or arms, something like that. It was only really Huygens, exactly 200 years before the essay competition. Huygens had a better observation, but he wasn't so good at composing anagrams, it seems. So this one turned out to be this Latin phrase, which revealed that it was a thin, flat ring, nowhere touching the planet. Okay, and then not long after that, Cassini noted the division of the main rings into two parts, the inner one being wider and darker. Okay, so by the time of the essay, well, this is what contemporary illustration of Saturn and its rings was in 1856. Now, by this time, the fainter inner C ring had been discovered. And indeed, there had been a revival of interest, it seems, in Saturn and its rings around about 1850, particularly in America. So the Bonds discovered the C ring, and there were discussions of the dynamics of the rings. Some possible evidence that Struve had found of some evolution in the inner part of the rings, which was, I think, controversial. And here's the diagram of Saturn in Maxwell's essay. So in those days, it's clear from the language in Maxwell's essay, and indeed the essay title itself, the competition abstract, that Saturn was regarded as a masculine object. But Maxwell also commented on how useless Saturn was. He was not aware of any practical use in astronomy or navigation of the rings, and it didn't have any effect on anything else in the solar system. However, it was most remarkable from the scientific point of view. Actually, he also says here that there's something even less useful than Saturn's rings. That's the spiral nebulae, in other words, spiral galaxies, which had recently been identified. But I sort of think maybe that Saturn itself, the planet, was thought of as a sort of ivory ball, like one of these in the mechanical model that's been on display here. Okay, now in Maxwell's essay, he pays homage to Laplace, the great mathematician, and refers to his great work, that being the treatise on celestial mechanics, published from 1798, or the year 7, as it was known in revolutionary France. So here are a couple of pages from Mécanique Céleste, Laplace's discussion of Saturn. So the first result of Laplace's that Maxwell refers to is the fact that Laplace argued that Saturn's rings couldn't be a uniform solid ring because it would be unstable. So this is our first example of a gravitational instability. A uniform solid ring would be in equilibrium. The gravitational attraction between the planet and the ring can be balanced in this configuration, whether or not the ring rotates. But it's unstable, and it's not immediately obvious that if we move the ring sideways, well, parts of it will come closer to the planet, other parts will go further away. It's not obvious whether the energy is lowered or increased, if you want to think about it that way. We can look at this actually using Laplace's equation. If I'm allowed an equation here, perhaps Laplace's equation will be okay. So this describes the variation of the gravitational potential in regions of space away from where the ring is. This is the potential of the ring. Now, first of all, I should say that we're allowed to replace Saturn as a spherical object with a point mass at its center. We know that from Newton. The gravitational properties of the planet can be reduced to that of a point mass at its center. And so the question then is whether this point is sitting at a local minimum of the gravitational potential. That would make it stable. But Laplace's equation is telling us really that at this point, the potential due to the ring can be neither a maximum nor a minimum. In a sense, it has to be a minimum with respect to z, the vertical coordinate, because if we move the point above the plane of the rings, it'll certainly be attracted back downwards. So it's sort of stable, or a minimum in that dimension. And then, correspondingly, it would have to be a maximum with respect to the horizontal coordinates. And so it's unstable. And Laplace argued it slightly differently. Actually, what I just described is more based on Maxwell's own kind of reasoning in his essay. But Laplace concluded that the ring would be unstable to lateral displacements and would then collide with the planet. So it couldn't be that. Now, how else in astronomy can we consider a gravitational equilibrium? Because the thing about gravity is that everything attracts everything else. So how can you have an equilibrium of the forces? The uniform circular solid ring is a bit special in that regard. But another way we can achieve it is by having things orbit around each other. So if we consider a particle, or it could be a moon of Saturn, going around the planet in a circular orbit, that's a kind of equilibrium, although it's moving. We could look at it in a rotating frame that rotates with that circular orbit, and then it's just stationary at this point, and that's a kind of gravitational equilibrium. Now, if we displace the particle towards the planet, we think that's sort of releasing potential energy, that it's potentially unstable. But of course, it doesn't, because as we know from Kepler and Newton, it'll just go into a slightly elliptical orbit, which in the rotating frame of reference means that the particle, the moon, does a little epicycle around its original location. This epicycle is strictly an ellipse rather than the circle that the Greeks thought of, a circle on top of another circle, or indeed in Maxwell's model, I think it's a circle on top of another circle. But the point is that the energy can't be released because, well, either we can think of it as because of the rotation of the frame here, the motion is diverted from towards the planet into this loop, or we can think of it in terms of the conservation of angular momentum that blocks the release of energy in this configuration. Another result of Laplace's that Maxwell refers to in his essay is another aspect of equilibrium. This is really for a fluid ring around the planet. So let's think of this as a cross-section of a sort of elliptical tube that goes all the way around the planet. And the question is whether we can balance the forces at some distance from Saturn. So Saturn's away over here to the left, let's say. Now, if the center of this ring, it's a ring that's narrow and also thin, if the center of this ring is rotating at the appropriate speed for a circular orbit around the planet at this distance, and if the whole ring is actually uniformly rotating around Saturn, then the gravitational attraction of the planet on this part will be too great, and on this part will be too small. So there'll be a tidal force trying to shred the ring, to pull it apart. And that could be resisted by the gravity of the ring itself, pulling in towards the center here. And it's possible, as Laplace showed, to balance these forces together with a pressure gradient, but only if the ring is not too close to the planet. We could express it by saying a certain d is greater than 4.6. Well, what do I mean by d? It's a convenient way of describing either the density of the material of which the ring is made, that's why I called it d, but it's also a measure of the distance of the ring from the center of Saturn, actually the cube of the distance. So if that's sufficiently large, then it will be able to hold itself together against tidal forces. Now, Maxwell would go on in his essay to discuss various stability conditions which could be converted into critical numbers for this parameter d. And in a sense, they were to do with comparing properties to do with mass with properties to do with the rotation, which is the omega here. Now, interestingly, at around the time of Maxwell's essay, some related work was done in France, but it wasn't apparently known to Maxwell or the British community. That's the work of Edouard Roche around about 1850. Now, this differs from Laplace's work. Roche was thinking of an ellipsoid, the sort of rugby ball-shaped three-dimensional figure, which we could think of as maybe one of the moons of Saturn, which had drifted too close to the planet and was also being potentially torn apart by the same tidal forces, but in a three-dimensional way. And Roche showed that you could sustain such a fluid body, but it had to be even further away from the planet in order for the tidal forces not to be too strong. And indeed, Roche proposed this as a way to form the rings, that a satellite that was too close would be torn apart and into rings. Now, if we place these, try to place these distances on this beautiful image of the Saturnian system as we have today, a montage of Cassini images, well, if we assume that the ring is made of water or water ice, something of that density which is greater than that of Saturn, then Roche's ellipsoids could exist outside a critical distance which roughly here. So that'd be consistent with the idea that you could form the rings by breaking up objects at about this distance. Laplace's uniformly rotating ring, the sort of elliptical tube, could exist outside this distance, which, as it happens, is close to the inner edge of the B ring. I mean, there are other ways to think about this competition between gravitational attraction of the ring material and tidal forces. For example, if you had strong, solid, spherical particles, you can ask if they can stick together through their own gravitational attraction, which they can do outside a critical radius, or whether little particles can stick to big particles, and so on. These are other ways of thinking about this criterion. So actually, the first problem that Maxwell solved in his essay was building on Laplace's theory about the uniform solid ring, which had been ruled out. What about a non-uniform ring? Now, this is a really difficult problem, which I guess the wranglers of the day would be good at doing. But it's actually, I find it quite difficult to reproduce this calculation, I must admit. But Maxwell set it up in a very clever way and used Fourier analysis, which, as I think Malcolm mentioned, he'd read about in his youth, to describe the angular variation of the density of the non-uniform ring, and then derive conditions on the stability of this configuration. In particular, he considered an extreme kind of non-uniformity. So Laplace's uniform solid ring mounted with a heavy particle at one point. And Maxwell concluded after lengthy mathematics that even this would also be unstable unless the ratio of the mass of the particle to the uniform part of the ring was in this very narrow interval, which seemed highly improbable. And so that basically ruled out the theory of the solid ring. Perhaps the most well-known aspect of Maxwell's essay was about the stability of co-orbiting particles or satellites. So this is quite a good way to set up an equilibrium configuration whose stability can then be tested. So we have a number of identical particles or satellites following the same circular orbit around Saturn, and then we ask whether that is stable or unstable. So, as was suggested in the previous talk, this was done by linear stability analysis, introducing small perturbations from the equilibrium, simplifying the equations in that way, and using Fourier analysis to describe the various undulatory modes of the system, as are beautifully illustrated with the mechanical model. And he had to consider radial, tangential, and vertical displacement. So in this direction, away or towards from the planet, in the direction away or towards from the neighboring satellites, and vertically out of the plane. And the complication of the problem is that the radial and the tangential ones, the ones in the plane of the ring, are coupled together by the rotation, which we noted in the discussion of epicycles. And so here are some illustrations of different Fourier modes, different numbers of oscillations in the configuration. And Maxwell showed that the most dangerous ones, the ones most likely to be unstable, were ones in which the neighboring ring particles would undergo equal and opposite displacements. And indeed, he showed that the ring would be unstable if this criterion was satisfied. Now, this can be interpreted as saying either that the ring, so I should say MP is the mass of a single particle, n is the number of particles. This is a condition that the ring be sufficiently massive, or alternatively, that the number of particles be sufficiently large. So if there are too many particles, in a way, if their spacing is insufficient, then the system will be unstable. I'll come back to that one. As for the outcome of the instability, Maxwell described in detail the growth of the unstable modes in the linear theory that he had, but he could only speculate about the eventual nonlinear outcome. But he was quite right that it causes the particles to collide with each other, and then they can stick together and form fewer, more massive satellites. So, I mean, this illustrates the sort of spiraling trajectories of the unstable motions of neighboring particles in an example of this unstable mode leading to a collision between particles. And then Maxwell tried to relate this, at least qualitatively, to theories dating back to Kant and Laplace in the 18th century about the formation of planetary systems, the origin of the solar system. So, yeah, a few years ago, we actually did a simple numerical simulation of this instability to show that the particles do indeed collide through this instability, and they stick together, or if they're allowed to stick, they can form fewer, more massive objects. Okay, now the modern view of Saturn's rings, thanks to the Voyager and Cassini missions and other ground-based investigations, is that they are indeed composed of very large numbers of particles of almost pure water ice, so trillions of particles, which are orbiting the planet at like 10 kilometers per second or so, and relative to that circular motion, they have very small random motions on the order of millimeters per second. Those are the characteristic speeds at which the particles are gently colliding. And indeed, there is a tendency for them to clump through their own self-gravity. So, well, we have both computer simulations and oil paintings describing this situation. We don't, even Cassini isn't able to image the individual ring particles, but we do know something about their size distribution. So this is, provides some structure in the rings, not necessarily forming bound objects, but contributes to their activity and dynamics, sorry for the spelling mistake, and also provides a transport process within the rings. Now, Maxwell did somewhat briefly consider the possibility of fluid rings, his calculations in this area have been noted to be flawed. In fact, he was aware of this himself, I think, but he did conclude qualitatively that the gravitational attraction of different parts of the ring would cause it to break up into beads, as he described it. So, the modern theory of gravitational instability in fluid disks and rings, which might be gaseous rather than the watery disks that he was thinking of, do indeed provide a condition on the ring or disk to break up into clumps or fragments. This work was done in the 1960s, particularly associated with the name of Tourmaret, but also by Goldreich and Lindenbell here in Cambridge. And I suppose that what's going on here is that we're finding a way of rearranging the material so as to bring things closer together, so releasing gravitational energy, but respecting all of the constraints, which here are to do with the conservation of angular momentum, or to incorporating the fact that this is all a rotating fluid. And applied to Saturn's rings, at least in the sort of watery models that Maxwell was working with, that would occur at quite a close distance to the planet. So from somewhere about here onwards, a watery disk would tend to be gravitationally unstable. And indeed, we know that gravitational instability of the icy rings is active in the outer part of the ring system, increasingly so as we get to the outer edges. So among Maxwell's conclusions to the essay were that the only system of rings which can exist is composed of an indefinite number of unconnected particles revolving around the planet with different velocities according to their respective distances. He expressed it more poetically in this letter to Thomson. What shall we say to a great stratum of rubbish jostling and jumbling round Saturn without hope of rest or agreement in itself, till it falls piecemeal and grinds a fiery ring round Saturn's equator? Yes, so the main thing neglected in Maxwell's analysis of gravitational instability was the orbital shear, because he was thinking in a way of Laplace's uniformly rotating rings, but they can only really be narrow, not the broad rings he wanted to think about. And also in the same letter to Thomson, he expresses his concerns about orbital shear in this way, that he wouldn't recommend anyone to few a building stance on any of the rings, because the parallelograms would be spun out into spirals in a few hours. And indeed, the way we analyze gravitational instability in disks which are subject to orbital shear, that's the inner parts are rotating more rapidly than the outer parts because of Kepler's laws, is very much builds in that sort of deformation, that shearing into the wave analysis. Now, I was very interested reading Maxwell's essay to see what he says about the viscous spreading and evolution of the rings, which is not quite the same thing as stability, because I think when the essay topic was set on stability, the idea was, well, Saturn's rings have been around for at least 200 years. They are stable, clearly, in a dynamical sense. It's much longer than the orbital timescale. But here we're looking at how they might evolve over very long timescales. And he was thinking both about particles which would collide with each other because of interactions and resonances between differently rotating parts of the system, and or of a fluid ring where there'd be a viscosity which would, either of these things, collisions or viscosity, would tend to dissipate energy while conserving the angular momentum, which in those days had to be capitalized, of the system. In particular, for the fluid ring, he derived this equation for the rate of change of the energy of the ring, which is essentially orbital energy as a result of viscous dissipation working on the orbital shear in the ring. And using Stokes's value for the viscosity of water for the purposes of illustration, he concluded that the energy of the ring would change on at a timescale this number of years, which was inconceivably longer than the age of anything as considered in the mid-19th century, well, and even now, longer than the age of the universe. But Maxwell noted that this process would cause the ring to spread. So the inner radius would go inwards and the outer one go outwards. So this could be seen as foreshadowing the theory of accretion disks, which is really a 20th century development with wide applications in astrophysics. Now, we can actually measure the viscosities in Saturn's rings by looking at the waves excited by the moons. So moons out here at various resonant locations in the rings excite waves, and those waves travel some distance and then they're damped out by the viscosity of the rings. And estimates of the viscosity, something like 100 to 1,000 times that of water, which Maxwell was considering, depending on which part of the rings you're looking at. And that actually would give you evolution timescales similar to the age of the solar system. That isn't necessarily helpful because most people think that Saturn's rings are much younger than that, perhaps only hundreds of millions of years old because of their purity. So there are still puzzles there about the evolution of the rings. So Saturn's rings can now be seen in the context of other astrophysical disks around stars, black holes, and so on. Of course, they're an extremely beautiful example, one where we can resolve in amazing detail things like the interaction between objects like this moon, Daphnis, in the outer part of the A ring, how it interacts with the rings by opening up an annular gap through the excitation of these edge waves. And a closely analogous process happens when planets are born in gas disks around young stars. If they're sufficiently massive, they can open a gap. And the ways that they excite in the surrounding gas disk carry away energy and angular momentum. These processes are fundamental in understanding how planets attain their final mass and their final orbital configuration around, well, our star and other stars. So what about the outcomes of gravitational instability? Well, indeed, it's possible to form objects by agglomerating material, as Maxwell supposed, but another possibility is, that, as we've seen, forming structure and transport within rings and disks. Now, looking at the Saturnian system with a wider scope, there are many rings, there are many moons outside the ring system, and some have speculated that actually, instead of the rings being formed by disrupting moons here, you could work the other way, that the outward expansion of the rings could lead to formation of moons at the Roche limit, and then they get pushed away. I mean, the boldest version of this theory, which I would say is not widely accepted, is that all the moons in the solar system could have been formed from tidal disks like this around planets and produce different numbers of moons depending on the properties of each planet. Now, going back to the planet formation in disks around young stars, gravitational instability is seen as being important in the early phases, the first few million years, when the disks are massive enough to satisfy that instability criterion. And depending on the thermal properties, how rapidly the gas can cool, this is thought either to produce bound objects, which might be very massive planets, or alternatively to produce structure, spiral structure, a recurring set of density waves. So the first process could plausibly explain some of the most massive and distant planets. So, I mean, this is the distribution of exoplanets that have been discovered in recent years, the ones of many Jupiter masses that are far from their stars. Some of them might have been produced by gravitational instability. Otherwise, gravitational instability can play a role in the formation of other planets, for example, in helping things to form planetesimals within the gas disks. But the second possibility, this one here, which here is seen in the context of protoplanetary disks, that theory was developed in the 1960s to explain the spiral structure of galaxies. So that's an outcome of gravitational instability in another type of astrophysical disk. Now, I'll try to draw some other connections with Maxwell's ideas, because looking at some of the correspondence or some of the documents coming shortly after Maxwell's essay, it's clear that he was trying to develop a kinetic theory of the rings there. So considering these very large numbers of colliding particles. But this kinetic theory is much more difficult than the kinetic theory of gases he would go on to develop, where the particles just go in straight lines between collisions. Here, between collisions, the particles are going in Keplerian orbits around the planet, and there might only be a few collisions per orbit. Also, the collisions of the particles might be quite inelastic. They don't just bounce off each other in an elastic way, as in the standard kinetic theory of gases that he would develop. So Maxwell, I think, aborted this plan. It was only carried out in the 1970s and beyond. This kinetic theory of colliding inelastic particles in the context of an orbital shear flow, as in an astrophysical disk. And that sort of theory can be roughly matched with the computer simulations of very large numbers of colliding particles in local models of such disks, including Saturn's rings. Now, other types of astrophysical disks that we study include the high-energy plasma disks around black holes, which are also dominated by orbital motion around a central point mass. But the physics is rather different. I mean, here, this material it's very hot, it's highly conducting, fully ionized, and the magnetic field plays an important role in the dynamics, the subject of magnetohydrodynamics, sort of fusion of fluid mechanics and electromagnetism. And I think Maxwell would really have enjoyed magnetohydrodynamics. It has appealing mechanical pictures. The magnetic field lines, or the lines of force as he would have called them, move with the plasma. That's a famous result due to Alfvén, who won the Nobel Prize for his work on MHD. And also the magnetic field affects the motion of the plasma through magnetic tension and magnetic pressure. I mean, putting those ideas together, we get this mechanical picture that the magnetic field imparts an elasticity to the fluid or the plasma. And indeed, those ideas of tension and pressure, the way the magnetic field influences, for us, the fluid flow, is described nicely by the Maxwell stress. He describes in this, in his textbook, the tension and pressure due to the magnetic field, which we now think of as a stress tensor. But we can also link this to Maxwell's work on viscoelasticity. There's something called the Maxwell derivative, which derives from his work on the time-dependent relation between stress and strain in what we now call a viscoelastic medium. And I mean, nowadays we can express this in a tensor language, which Maxwell didn't have. But it turns out in MHD, the Maxwell stress evolves in time through what we would call a Maxwell derivative. So that's a nice connection. Now, coming back to the exoplanets, there's an interesting variant on one of Maxwell's problems. We could consider equal mass satellites, equally spaced in a certain sense, orbiting, well, it could be a star in this case. These might be planetary embryos on the way to becoming planets. They've formed in a gas disk, and they're competing in some sense with each other. Now, the question is whether this is stable or unstable. Well, that turns out to be an unfair question because it's not really an equilibrium to begin with. These planetary embryos want to orbit the star at different rates, faster on the inside, slower on the outside. And so they will have close encounters at various times. And these close encounters cause random kicks or semi-random kicks in their orbital properties, in particular their eccentricity, which can undergo a sort of random walk process, leading eventually to a collision and a merger between these objects. So it's not as clean as Maxwell's problem. There's no clean separation between stability and instability. It's more about the time scale, which depends exponentially on the separation of the particles expressed in a certain set of units. If we convert Maxwell's problem, which was for satellites on the same circular orbit but separated in the tangential direction, then, well, basically where they would be unstable in Maxwell's problem, this protoplanetary system will lead to a collision on quite a short time scale. Otherwise, it could last for millions of years. So this kind of consideration is very relevant in understanding the architecture of planetary systems, including the solar system. How full is it? Is there room to put in another planet, or would it just lead to instability in the sense that we've described? But also there are many interesting exoplanet systems that have been discovered with multiple planets, like 7 or 8 planets, such as Kepler-90, TRAPPIST-1, and so on. And this kind of consideration about the dynamical spacing and the fullness of planetary systems is very relevant for understanding how these can be formed and how they are stable. And a further connection, which has been already discussed in the previous talk, is about stability, polynomials, and so on. Because at several points in Maxwell's essay, he determines the stability of a certain mechanical system through the linearization of the equations. And then, well, as he says here, let us write n instead of the symbol d by dt. So he's expressing the time variation in terms of a parameter n, which is equivalent to saying that the small perturbations are assumed to depend in an exponential way on time. And this number n might be a complex number, or an impossible number, perhaps we should say. And he then determines algebraically whether or not the roots of this polynomial equation imply growing disturbances or not. So this was later to be more systematized through his own work, which, as we've seen, led to the field of cybernetics, but also through Routh's work, and as the previous speaker described, the Adams Prize, much later in 1876, for which Maxwell was one of the examiners, was on this topic, where Routh was able to solve this problem quite completely. Also, the Fourier analysis, this way of analyzing disturbances, well, for Maxwell's ring system, that was taken forward by Thomson and Rayleigh as linear stability analysis of shear flows in fluids. Okay, so to bring this to a conclusion, we can certainly agree with Airy that this Maxwell's essay is a remarkable contribution to mechanical astronomy, but arguably it's quite a lot more than that. It's inspiring, I think, because it's both a broad investigation but also a deep one in several places. And Maxwell shows quite a pragmatic use of simplifications and approximations to make the problems tractable. And he remarkably is able to extract or extrapolate the physical conclusions correctly from these carefully chosen model problems, and I found that very inspiring. And as we've seen, in many ways, Maxwell's essay anticipates a number of developments that were to come even a century later. And there are plausible connections with his remarkable developments later in other fields such as kinetic theory, stability, and control. And I think also this work and the correspondence surrounding it reveals a very human genius, perhaps more Beethoven than Mozart. He clearly struggled with early calculations in this essay and yet produced a remarkable work as a result of it. Thank you.